I know, I was like, looking. I was like, oh my gosh, I don't have to get up early at all this week. We have lab.
Yeah, that's another thing.
I can sleep in all week.
Any summer plans, Taylor?
Oh yeah, I'm going, we go to CHEM every year for about a week and a half in July.
Oh, nice.
And then I'm going to Boston in August.
Oh, what are you doing in Boston?
Meeting my boyfriend's family.
Oh, nice. That's cool.
Yeah, I'm so excited. And then, we go to Lake of the Woods at least twice a month during the summer, and then just like Lost Creek and all around.
Nice.
I used pastor in the church I grew up at had a cabin at Lake of the Woods, and we would go out and go tubing.
Oh, that's cool.
Have a bonfire. It was awesome.
Do you have any plans this summer?
Not particularly, but I do want to like kind of explore the watering holes more.
Oh my gosh, they're everywhere.
Yeah.
Waterfalls all over the block around here. It's crazy.
Oh yeah.
Yeah, and I need to hike more.
I tell myself
Watch
when
out
I
for
get to the
ticks.
mountain and want to get out. Right. I would like it if I was hiking to like a waterfall, like up in Washington,
you could
but
just,
it's
like,
really hot and you just get
Take
in
a
water.
dip in the waterfall. There's a few of them around here.
Yeah,
You
what
gotta
is
drive
it?
a little ways to get there.
Like the Mills Creek Falls or something?
There's like a whole you can do within a day. Yeah. Oh.
I want to take a couple weeks off work and go like all the way to Washington and all the way back down to Cali in just like 2 weeks and go to other places.
Yeah, Burning Falls in California is pretty cool.
Yeah.
Burning Falls. It's like right it's like right over the border or somewhere. I can't remember exactly where it's at, but it's pretty cool.
And then I have a couple friends down in Cali, so go see them. Stay on like
Where's their beach house at?
I couldn't tell you.
And
It's-
like NorCal, SoCal?
It's by San Francisco.
Oh,
I think
cool.
it's like 5 miles north of San Francisco.
Oh, that's pretty cool.
I've never been to San Francisco.
Yeah, me neither.
My stepdad and my mom go all the time. Every weekend, I'll just drive down.
Every weekend?
Not every weekend, but just for fun.
I don't think you could.
My stepdad grew up in Burbank, so he knows all the spots all the way up and down.
Yeah.
I'll never forget the first time they went to Tahoe. They came back and they were like, "We're moving to Tahoe," and I was like, "Yeah, good luck
I
with that."
love Tahoe.
Like,
Yeah.
Mom, you can afford Tahoe even if you won a lottery.
My mom and I used to do competitive soccer for the Timbers, and we had a tournament in Reno. And
That's awesome.
and my mom and I, we drove all the way down in her minivan, and we got into the secret beach on Tahoe.
Oh,
And we
nice.
had to like sneak through the gate in her van, and we just looked so poor. We
had a-
compared to everyone. The
Because everybody's all in their
Oh,
fancy
yeah.
clothes.
The cheapest car in there was probably Corvette. Like,
Oh, my
it was
gosh.
Oh, man.
ridiculous.
That's
We had a family reunion camp out in a campground right outside the Olympic Village. I can't remember what the name of it is now, but it was pretty cool. Mine had never been into a casino before. My mom was like, "Let's go," and I was like, "Okay." And so we went into a Harrah's.
Nice.
She stuck $20 in a Wheel of Fortune machine, and she walked out there with like $300. I was
Oh,
like,
so
"Okay." She's like, "Don't get confused. That doesn't happen every time." I was like, "Okay, well you got lucky then."
That's cool.
I was into Vegas and those casinos. I told my mom every match that I win, I was wrestling, I would get to put $100 on my bread on a roulette. I lost all my money. It was a really tough tournament, so I
Very
figured I
careful.
won
Oh, yeah, you really might as well.
it. Lost to a kid from like the East Coast, and then I should have won the second one, but he got lucky.
Ooh. It's crazy to think, like, I feel like spring just started and also
Oh,
it's
me
almost
too.
over already.
It's making me lose my mind.
Doesn't help that summer feels like it takes up such a big chunk of the year nowadays. Remember when it was only hot for like July, June, and August, and then now it's like, all right, it starts getting hot at the end of April, and then it's hot until October.
I just hope you don't have a smoking somewhere.
Unfortunately, I think it's gonna happen. Get nearly enough rain and snow so we can I'm out by.
Good
I know, I have some
vibe.
friends up in Washington, I'm like, I'm gonna go hang out with you guys.
I wanna do, have you seen the United States, like, tour, like the perfect road trip, like all around, that
My
hits all the.
grandparents were gonna
islands?
take us, we ended up getting to Minnesota, we had to turn around because the tow vehicle got totaled.
Oh,
And my brother got super sick, like tow vehicle got totaled like right off the bat, somebody left it in reverse.
Oh.
And as we're pulling out of the driveway and going down the road, my mom calls us, cause she'd followed us to go home, and she was like, is the tow vehicle supposed to be smoking? And we're like, oh. But instead of canceling the trip and getting the tow vehicle totaled, because we had all these reservations, my grandpa was like, well, we'll figure it out along the way. So that was fun. We got to see the Mall of America, which was pretty cool.
I haven't been there.
And then the next year we got to go to Disney World because we still had Disney World tickets, and my grandma was like, we are not getting refunds on those, so we're gonna have to go.
Where's that mall?
It's in Minnesota somewhere. I can't remember exactly where, but it's pretty huge. It's like the size of this. And we'll have like a theme park inside of it too. It's crazy. There's like 3 or 4 Disney stores. It's crazy. It's huge. The food court's the size of our mall. It's insane. Yeah. Nothing makes our mall look more pathetic than other malls.
Our mall always looks so sad.
Everything's like dead in there anyways. It's so sad.
I'm like, oh, I love malls, why are they dying?
The Washington Square Mall up in Beaver is pretty nice.
I hate walking around the mall, so I couldn't
Right,
imagine
there's always
walking
so
in
many
like a
freaking
huge
people.
mall.
I think this is what's cool though, like they had gondolas inside, like the madness. It was really weird, cause like, it looked like you were in the open and it was like modeled after a little city, but
Right.
inside. They have a lot of cool stuff. Our mall's kind of boring.
Kind of.
But really,
Our mall
I like
is a lot
these
more.
things.
We don't even have,
Yeah.
last time I was in there, the arcade is gone now and the laser
Yeah.
tag, so it's like, that sucks.
How did that close? Like,
Nobody's ever in there.
I feel like people were always in there.
yeah, I thought
I
people
never saw
went.
people in there. Well, and I used to work right across the way and I never see anybody in there. Because I worked there when it was Master Cuts too.
Oh, yeah.
So, yeah.
I can
Our
never
mall's
work
just
in
dead
a
as
mall.
hell now.
I need windows and I need a light.
Yeah, they got some big skylights right out on the walkways, but yeah, I get it.
it's just neat to see like the downstairs ones.
Having to be on lockdown at a mall is a fun time.
Oh, that sounds.
A couple of different times when I was in Master Cuts, had the security guard go by or call us and be like, you need to shut the gate and hide in the back now.
Oh,
Because
that's
there'd be
not.
like people with knives or something. I'm like, okay, we don't have another way out of the salon, so we're stuck here.
It's not fun.
You actually did that. Oh yeah, they're also doing more. Yeah, they do
Oh.
Are you ready for the Spanish exam?
All right, let's hop to it. So first of all, check your grades. So I should have caught up on everything that was handed to me, so everything should be accurate. I'll hand that back today. But just make sure that I didn't miss anything or, yeah, there's no hidden stack somewhere, although, like I said, I went through all my papers this weekend trying to catch up. So I think I'm caught up, but let me know if something is still wrong. And so let's talk about your final just a little bit, or at least the format. And so right now it has 8 multiple choice questions. And then let's see how many free response. So 1, 2, 3, 4, 5, 6, 7, 8 free response. And we'll go over the types of free response. And then there's also one bonus that's 5 points. And we'll go over the bonus as well and how to approach that one today. All right, let's just dive into it. So our first question.
So is it like only 17 answers?
Yeah, so only 17 questions.
Questions.
Short final.
Well, 8 free response.
Well, yeah, but as opposed to 100 questions like every other final is.
Yeah.
No, I'm saying that's awesome.
All right, let's try the first type of practice problem. So, oh yeah,
Is this for viewing posted?
not yet, but I'll post it right now. So see if you can write the equilibrium constant expression for the following. So we have 2a plus 3b gives us a2b3.
If you want to make a trade,
What?
if you want to make a trade.
You have favors for me? That's not really present. I think your name is missing. So do we have an answer? Need more time? So do we have an answer for this one? Can I remember what this was? What's kind of the general expression for our equilibrium constant? Like if we want to make it really general. So our Kc, which is equal to what? Yeah, so products over reactants, so that's what I meant by really general. And then if we remember right, we have to take all of these concentrations to the power of their coefficient. So then we should have something that looks like this. So our product to the power of 1, since we only made one equivalent, and then over our A squared, and then B to the third. And so let's take this one little step further then. And so now we'll ask, so find the K then at equilibrium. if the concentrations are the following at equilibrium, so 0.22 molarity for A, B has a equilibrium concentration of 0.33, and then our product, sorry, let me rewrite this. Bless you. And then our product, A2B3, if its concentration is 0.11 molarity. So what is a K? What does that mean? See if you remember how to do that. And so this one, what do we have to do to solve then for our K? So yeah, plug in the values exactly. And so now we just have to, right, plug into that expression. So now we'll plug it in, so I'll just rewrite our equilibrium expression. And we get something, so 0.11 over 0.22 squared times 0.33 cubed. And so what do we get for our number when we plug it in? $63, that sounds good. Is that what other people got? So I get 63 as well, so just make sure, right, you do order of operations, and if you enter it in, so I put everything in one calculator line, making sure you put parentheses around the bottom, so it does all that first.
And that number doesn't have a unit of measurement?
Yeah, correct. So yeah, equilibrium constants don't have any units. So it's just kind of, again, our measure of our product to reactant ratio roughly. Excellent. Questions about this one? So this is the most that you're going to have to do with the equilibrium expression is, right, just translate it to a K value and then maybe plug in numbers, you know, maybe not. Just kind of showing that just in case.
What did you get for it?
Oh, like 63-ish or,
63.24.
and yeah, just watch your parentheses. Make sure you squared the 22 and cubed the 0.33. And I can look at your calculator while we're working if you need. All right, so let's try the next one. So of course we're going to have some gas questions. So let's just try this one and see how we do. How's this problem coming along?
So do you use PV equals nRT, or would you use, that would be the ideal gas law, would you use one to find the moles?
Yeah, I'd probably use PV equals nRT.
And then for R, would you look at
Yeah, so what R is that again? Because it's our gas constant, but then what's the value? 0.0821. So again, right, star that, whatever. This is the one for the gas, for the PV equals nRT. And then what other things do I have to be careful of before we just plug everything in?
in Celsius,
So,
convert it to Kelvin.
good. You guys are on the ball. So adding 273. So again, right, you're welcome to take the more precise 273.15, but given the sig figs, I usually ignore that. So it looks like 345 for our Kelvin temperature. Excellent. So I think we're ready to plug it in. And so let's see, what are we solving for? So we have pressure, we just need moles. So I'll just start.
So would it be PV over RT? Would you do it like that?
Yeah, so you could rearrange it. We'll do that. So PV over RT equals N. And so just start plugging in our variables. And everything else is good, right? ATM liters, so that matches with our R constant. Oops, sorry. So then, do we get this many moles of our gas here? So plug that in, and I get 1.02 moles. Does that sound good?
Yeah.
Do other people have questions?
What would be the significant figures? Would it be 2 or 3?
Yeah, we only have 2 here, but I'll probably, so I'll still report this to 1.02 moles for now, and then we can round to like 1 for the final answer, but I don't want to drop it too early to get to the mass here. And so then our mass, the key, of course, is that it tells us that it's nitrogen gas. And then we also have to remember that nitrogen is our diatomic, N2. So then what's the molecular weight of nitrogen?
14.007.
So then 14.007, but that's for 1 nitrogen, right? And then so times 2, since again it's a diatomic, so 28.014 for its molecular weight. Again, you could go rounded, right? 28 is fine. Not. And then to get our final mass, so times 1.02 and about 28.6, but then if you round it, so 2 sig figs, you might get 29 or 28, so that's okay with our rounding there. And so let's write out the work, so then multiplying it by our molecular weight. questions on this problem?
So how you start out is you get the molecular weight of the nitrogen gas, and then you use the 1.02 and just multiply it together.
Yeah.
And that gets the, okay.
Yeah, because, let's just recap, right? So first, we found our moles of our gas, right, using our PV equals nRT. We solved for moles. That's how we got this basically 1 mole of nitrogen, and then, yeah, just multiplying it by the molecular weight to get the mass there. Other questions, comments? All right, let's try, and I have to give you a reaction. And so we're reacting silicon tetrachloride with water, and it gives us HCl and silicon dioxide. And so the first thing would probably be to balance this equation, since I didn't necessarily give you a balanced equation. So balance the equation. And then once you've balanced it, see if you can go ahead and answer the next part of the question. So given the 7.11 grams of water and 8.93 grams of silicon tetrachloride, what is our limiting reagent? And then, of course, what's the theoretical yield of our silicon dioxide blast? So what's the balanced equation? And then I'll give you a few more minutes to work out the rest.
2 waters and 4 HCl.
So 2 waters, 4 HCl's. So that looks good, right? 1 silicon, 2 water, or sorry, 2 oxygens, 4 hydrogens, 4 chlorines, 4 chlorines. So that looks balanced. All right, so keep working. Just wanted to make sure we all had a balanced equation. Yeah, yep, so same thing, right, open notes, open everything. Just not open your partner.
Not open Google.
Yeah. Don't directly Google. Although sometimes those AI answers give you really weird stuff, so.
I know, sometimes Google's not correct.
I've heard recently that ultimately he rocks.
What?
Yeah.
Awesome. Natural selection at its finest.
So how's this problem going? So let's do at least part of it together. So what do we have to do? Let's kind of walk through it, right? So they gave us water, and they gave us silicon tetrachloride. Yeah, so right, we have to do kind of our moles things for each one. So we have a lot of math, but yeah, that's kind of the idea, right? We need to go from our mass to moles then of each of these, right? So we'll start with the water, and then we'll compare our mole ratio. So, and I would kind of focus, right, it asks us the theoretical yield of silicon dioxide, so let's focus on that, right, with our mole ratio, and then try to figure out, moles of silicon dioxide. So let's walk through that then. So let's start with our water. And we were given, 7.11 grams of water. So then how do we go from mass to moles again? Yep, so 1 mole of water, and then what's the molecular weight of water then?
18.016.
So good, so now we divide, and we can take this step by step. Oh, where'd my calculator go? There it is. So then first step, write 7.11 divided by our molecular weight, so 18. And so now we have 0.395, I'll just round there. So 0.395 moles of water. So I'm just writing right what we get from that step. And so then let's continue. So now that we have moles of water, we want to compare it to our silicon dioxide, right? So I highlighted what we're doing. So we need to compare. And so from our balanced equation, we say, well, 2 moles of water gives us 1 mole of product. And so we could set that up next. So our mole-mole ratio. So we have moles of water. And so now that goes on bottom. So for every 2 moles of water, we can only make 1 of silicon dioxide. And so now we can just divide this by 2. And so now we get 0.197 moles of product. So moles. So does that make sense for the water part?
So we're seeing, the amount of water that's used, how much of, would that be the theoretical yield of?
Yeah, so we've calculated
Outside?
our theoretical yield, exactly. But we still need to find our limiting reagent, right? So we don't know. So the 0.197 was just when we took our moles of water, right? So yeah, so we just did our mole-mole ratio there.
So then if the ratio was different, it was like 1 to 3, then we divide the 0.395 by 3.
Yeah, so if we had like,
So on and so forth.
yeah, so it's whatever our ratio. So yeah, if this had been a 3, we divide by 3. Or if this had been like a 1 to 2, right, we would multiply by 2.
Okay.
And so now let's do the next one. So maybe take a minute, see if you can figure that out on your own before we reveal it all. So what do we do? Kind of repeat those exact same steps we just did, just new molecular weight, right? So let's hear how your numbers are going. So now we'll just do the same thing, right? So we'll start with our 8.93 grams of silicon tetrachloride. So now we need to go from grams to moles. So what's the molecular weight of silicon tetrachloride?
76.03.
76? Yeah, 169 sounds. Do you have a decimal after
I
that?
got 169.898.
89 or something. Yeah, that sounds good. And make sure you multiply the chlorines times 4. So then 1 mole, you got the same. So then we can divide. So 8.93 divided by our molecular weight. So 169.89 or 898. And so now we have 0.0525, so that's moles of silicon tetrachloride. 0.0525. And now we go to our mole ratio. And so what's their mole ratio? Yeah, 1. So 1 to 1. And so I'll write the work, right? So for every 1 mole of silicon tetrachloride, we can make 1 mole of our silicon dioxide. And so this just ends up being our answer, right? So times 1 gives us 0.0525, or I guess I should have rounded to 2.6. And so now we can compare our answers. So looking at these, which one's our limiting reagent? Yep, so our silicon tetrachloride. So this is our limiting reagent. Since it made, right, fewer moles, so it's going to run out first. So this is the reagent that's going to be consumed faster than the water. So say fewer moles. So yes, this is our limiting reagent. So this is how much we would make. And then they didn't ask us necessarily whether the theoretical yield was in grams or moles, but let's at least convert. So convert 0.0526 moles of silicon dioxide to grams. So we could do that, so 0.0526 times, and then, does anybody have the molecular weight for silicon dioxide?
That was the 76.08.
76?
Or do you mean 92?
Oh, no. I have a different number, but mine might not be correct. What's the molecular weight of silicon?
28.086.
And then plus 32. So I get like 60.
I like 60.09.
So 60.09. I like that. You say you got 62, Kimmy?
I got 60.066, but I used all the numbers on the things.
Yeah, so that sounds good.
60-ish.
Yeah, so somewhere around 60, so you could round it to 60.1 as well.
Oh, 02.
Yeah, so O2. Oh, that makes sense. At least we know where you were. All right, so then multiply it. So 60 point, I'll do 0.8 or 0.9, I'll round it. So then if we wanted it in grams, we would have about 3.16 grams. And so we do have 3 sig figs at least, so. Other questions about this one? Yeah, so then this is now the theoretical yield in grams. Yeah, because we had, so basically, right, these are our two kind of theoretical yields or potential theoretical yields, right? We're calculating how much can we make based off of what we started off. And then based off of this one, right, we found, okay, this one was fewer, so this is actually what's going to happen. And then, yeah, all we did was convert this moles to grams, just in case. Does that make sense?
I remember, you didn't have to like divide by something?
Oh, that's only if it asks for like the percent yield.
Okay.
Yeah, because then, you know, we could take this a step further, you know, and say,
That's what I was thinking, because it's the actual yield times like 100
Or-
divided by the,
yeah, actual over theoretical. Yeah, so now we could say I isolated 3.05 grams, you know, in my reaction. So then what is my percent yield? So this is your theoretical, right? So this is always, because your theoretical is always based off of the stoichiometry, right? But in the actual, it's always like stated separately, right? Like, oh, in lab, you actually got this. Oh, you're talking about the rounding? Either way, so I think technically, I don't have it on the calculator, but I think it was 0.05256 or something. So then that's why I rounded it to 0.0226 later.
But then that SI, the CO4 is 0.0525, right?
Oh, it's because of rounding. So this is 525 like 6.
Are they both the same?
Yeah, so they're the
Oh.
same number.
Okay.
It's just I rounded it over here and didn't round it properly when I wrote it.
Okay, I just have to.
if you plug in the numbers for the percent yield, it's like 103. Because the actual yield is the 3.16 grams, correct?
Yeah, but then it's actual over theoretical.
Yeah, and then your theoretical was the, what was that one, the 3.05?
3.16 was our theoretical,
Okay.
and then the 3.05, right, is the actual. So then percent yield, so then it would be the 3.05, right, because that's actually what you have in your hand. Yeah, and then the 3.16, right, is always assuming perfect conditions, right, no loss of anything on the side of our flask, no randomly doing anything silly. And then, yeah, times 100 to get it as a percentage. And so, yeah, I think somebody said 96.5. So 96.5% yield. Other questions on this one? Actual. So this is right, like your actual, and then over theoretical. And right, so I'll just emphasize, so theoretical would be, so from stoichiometry. So that's always what you're calculating, right, is a theoretical yield, and then the actual you have to be told, because that's what you actually do in lab, you know, after you spilled half of it or whatever happens. All right, let's try another one. So now we have more gas laws. So we have an initial volume is at a pressure of 2.88 atm and 8.63 liters. So what is the volume if the pressure is increased to 5.21 atm? Do you have answers for this one? What equation did we use?
Pressure line times volume.
Yep, so P1V1 equals what? P2V2. Yep. And so don't forget also write the huge combined form, write your P1V1 over N1T1 is equal to P2V2 over N2T2 in case you need to derive anything else. And then of course, right, this simplified gives us this since moles are being held constant, right, temperature is being held constant, so that gives us our Boyle's law expression. And so then you just plug everything in. Units don't matter as long as they're consistent in this case. And so what do we get for our volume then?
4.77.
So 4.77. Does that sound good to everybody? So I see some nods. I'll plug it in really quick. So 2.88 times 8.63 divided by 5.21. So yep, 4.77, and then liters. Excellent. And then right, sanity check, you can always just kind of, double check. Well, we were at 2.88 ATM. If your pressure is increasing, right, you probably expect your volume to be smaller, which it is, so that all kind of works out. All right, should we take a little break? Yeah, let's take a little 10-minute break. I'll get the link up so you can follow. I just need to post the view link. So yeah, I'll probably meet back at like 2-ish in 10 minutes. And we just have to finish up with some pH anyways. So I think like Sunday at 5 p.m. if you're emailing me. Yeah, I prefer to have it on Wednesday just when I see you, but
I just wanted to make sure that'd be okay.
yeah. Yeah, I'd probably give it back to you like Wednesday, but I don't know, if you wanted it Tuesday, you could hunt me down like on my classes. So I'll be around tomorrow at like 11.
It might make it easier for you so you have less.
I think it's in the other
In
file.
this one, okay. Oxygen bases. What page is it?
16.
I didn't figure out this one.
I
But,
do have
okay.
my own.
But yeah, this one is the, and also this is page 11.
So I just looked at the homework answers, and this is supposed to be D, but I know that F is, excuse me, chlorine is really electronegative, and it,
But then highest boiling point, so you have to think about the forces, right?
yeah,
And all these are non-polar, since they're all, right, the same, they're all diatomic.
yeah, okay, so
So-
non-polar.
So then it just depends on their molecular weight then, the molecular weight argument.
Oh, okay,
So that's why it's iodine.
gotcha. So, yeah, because in my mind, I was thinking this wants to pull hydrogens, so it'd have like,
Yeah, but that'd be more for like HF. So once it's with HF, then it'd be really polar, and then that
Okay.
kind of thinking would work.
that makes
yeah.
sense.
We don't have well on our website.
Yeah, correct. No more, no labs.
Will you be in lab so we can meet there, or?
On Wednesday?
Yeah.
Yeah, if you want me to be there, I'll be there. And then as you start wandering back in, you can warm up on these two, so see if you can figure this out. So what's the molarity? What does pH have to do with molarity?
Acid base.
Oh, they're just in like,
random?
yeah, it's like
Should I
people's,
just-
yeah. How's this problem going? Do we have answers or thoughts, time? So how do we do this one? It's a molarity, so it's not grams over liters. So moles over liters. So that looks good. And so now how do we find moles then? Excellent. So let's convert grams to moles. And do you have the molecular weight then of HCl by any chance? 36.46. So 36.46, or again rounding is expected. So our 1 mole of HCl, 36.461 grams or so. Oops. All right, so then we get like 0.299 moles roughly. And so then you'd said it was moles over liters, and of course, right, I gave it to you in the milliliters, trying to trick people. And 1, 2, 3, so it's 1.437 liters. Oops, sorry, I drew that funny. 37. So then we take our 0.299 moles of our HCl divided by our 1.437 liters. And so I get about 0.2 for the molarity. Is that what other people got? I see a few nods. So about 0.208 molar solution. And then what's the pH? What do we have to do? What is that equal to? So that might help us for this expression, for the next problem. So that is a true statement. But what else is pH equal to? Like, what do we plug in when we solve for pH? Yeah, H3O, right? So the pH is equal to the negative log of our concentration of our H3O. And so that's just equal to that, right? And so this is a strong acid. So our HCl in solution, 0.208 molarity, right, fully disassociates. And so we still have 0.208 molarity of H plus ions. So then we just plug this number in. So right, whatever your concentration of a strong acid is, it's equal to your H plus concentration. So now our pH is our negative log of 0.208. We still might get a funny number since it is pretty acidic. And so I get a pH of 0.68, so pretty low. questions about this process? So now see if you can kind of repeat that and apply what you need to apply to this situation. So now it's asking pretty similar, except it's asking for our pH if we dissolve 0.766 grams of sodium hydroxide in our 956.7 milliliters of water. And then we already have our kind of helpful expression of this pH plus POH equals 14. So see if you can figure out where to go. How are we doing on this problem?
So we find the molarity first of NaOH.
Yep, so that sounds like a good start. So molarity of NaOH. And so again, right, molarity we said was moles over liters. So now we have to convert this 0.766 grams to moles. And does anybody have the molecular weight? So 39.997, that sounds good. So then we have 0.766 divided by the molecular weight. Bless you. So then about 0.019, I guess we could round it to 2. So 0.0192 moles of NaOH. And then you said, let's get molarity, right? So let's divide it by our milliliters, or converting it to liters, so 0.9567 liters. So now I'm just plugging in our molarity. Oh, 67. And so then I get a molarity of 0.02. So did everybody get that? So some yeses. And so now what do we do from here? So we have our molarity. What's this the concentration of as well? Hydroxide, excellent. Right, so now we can recognize that. So we have NaOH. And again, just kind of, think about what's happening. Oh, right, this can fully disassociate. And this is another thing. I probably won't do this. And by probably, I mean I won't, because I've written the exam. But this is something to think about. And so in our purposes, right, with our sodium hydroxide here, we only get one equivalent of hydroxide, right, when it disassociates. But if we were doing, so let's just, again, this won't be on your test, but it's good to mention. So let's say we had gotten 0.02 molarity of calcium hydroxide. So this one would be different because you would have to multiply it times 2 to get your hydroxide, right, since it makes 2 hydroxides when it disassociates. So that's the only part where it gets tricky. So then this would be, right, 0.04 molarity of hydroxide. So that's not what we're looking at, right? So they're just a 1-to-1 ratio. So in this case, yes, it disassociates, and it's still 0.02 molarity of hydroxide. Does that make sense?
Yes.
Yeah, so just comparing, right, the one equivalent versus any 2 disassociations. Again, I won't do this to you on the exam, so you don't have to panic, but, just going forward in your life, I want you to be aware of that. All right, so then we can skip to our POH calculation. So that's equal to our negative log of hydroxide, which again we have. We calculated that, so we can plug that in to our expression, our POH expression. So then we can solve for our POH, And so then I get about 1.69, or I guess you could round it to 1.7, but it's about 1.69 or so.
Typed into my calculator, negative symbol, log, 0.0192, and I got 1.7.
0.0192, that should be.
Yeah, I see.
It should be pretty close though, right? So 192. So if you had some rounding issues, right, you would still get 1.7 roughly for your POH. So that looks good. And then like we had said in the beginning, we have our pH plus POH equals 14. So then 14 minus our 1.7 or whatever rounded value. gives us a pH of 12.3. Questions about that one? Oh, so that was, right, we plugged it into this pH plus POH equals 14. So then I just did the 14 minus the 1.7. So let's try another one. So now see if you can do this one. So if we dilute 10 milliliters of a 1.11 molar hydrochloric acid solution to make 1.56 liters total, what is our pH? I could also like smell their sandwich wafting in. It's
Sounds
weird.
making me hungry.
Yeah, I was.
Everybody eat yesterday, get out of here if you're smelling good food.
How's this problem going? So what should we do first before we even worry about our pH? So find our new molarity. And then I was a little tricky, right, because I mixed the units of milliliters and liters. So it doesn't matter which one you pick, right, just pick one. So either you have to convert our 10 milliliters to 0.01 liters, so they match, or right, make this 1,560 milliliters. So it doesn't matter. And let's see, I feel like using milliliters today, so just setting up, so this is just C1V1 equals C2V2. So is equal to, and again, I picked milliliters arbitrarily to be in. So now X for our new concentration. So now I'll just solve. So 10 times 1.11 divided by our new volume. And so now I get this would be our new concentration, so 0.00712. So X equals that. So did we all get this for our molarity? And so now once we have our molarity, again, strong acid, only one proton, so now we can plug it into our pH equals our negative log of hydronium. So negative log of this. And so then I get about 2.15, I think, with rounding for our pH.
So I calculated in liters, and I got 7.2. I'm not sure what it went from.
So I'll put it in liters. So 0.01, did you do that?
Oh, I did 0.001.
Ah, so that would be, yeah, too many. So it's just 1, 2, 3 over, so yeah, 0.01 liters. So I think that should fix your issue. Other questions, comments on this one?
So that
Oh.
number,
Sorry.
so that number that you get, that's molarity, the first, M1 times V1 equals M2 times V2.
Yep, so then, yeah, new molarity and then pH of it. All right, let's try this one. So exothermic reaction, are our products lower or higher in energy?
What reactions?
The products, yeah, are they lower? So I think, so, yep, and so that's good, and so just a couple of things, right? So that would be my first thing to start off with if we're given an exothermic, so reactants, products, and then just start labeling it appropriately. So exothermic products are lower. And then it says our change of enthalpy in our reaction. And so then that means from reactants to products. So we want to label that. So delta H is 10 kcals. And other key points, so it says our activation energy is 15 kcals per mole. And so right, put that somewhere. So activation energy here to here. So EA, so 15 kcals, so that's labeled. So we have reactants, products, and then let's put, right, our transition state. So that's up at the top. We already put our delta H, we put our activation energy, and then we should just label our coordinates, so we can just say, right, reaction coordinate, and then energy is on the y-axis. Again, so this is for exothermic. And if this had said endothermic, really the only difference is then our products would be kind of up here. And again, just kind of try to label that. So with your 15 kcals versus your 10 there, the products. Questions about this one? You feel okay about this? All right, let's do one more review. So this is for the bonus problem. And so the setup goes something like that. So we're given this equation. And so this is one that we've seen before. And so now we're saying for the Haber-Bosch process, shown here, that the delta H of this reaction is negative 600.1 kilojoules. And so right, let's just stop for a second, right? So this is saying that this whole reaction involves this much heat. So that's evolving, right, our 3 moles of hydrogen, our 1 mole of nitrogen, and to make 2 moles of product. So just keep that in mind. So this scales with our moles of our reaction. And so now our problem is calculate the heat evolved when 2.36 times 10 to the 4th grams of ammonia is generated. Yeah. And so, right, base it off of what you're given. So you're given this information, right? So this is telling you that 3 moles of hydrogen plus 1 mole of nitrogen to give you 2 moles of ammonia evolves 600 kilojoules of heat. So that's what this is saying. So then it's now asking, find the heat if 2.36 times 10 to the 4th grams of ammonia is generated. So what do you have to do? Kind of think of moles and stoichiometry relationships. So I'll give you a few minutes and then we'll go over it. Tia. How's this problem going?
What a really big number is that when you see it.
Yeah, it should be big. And so what did you do?
Well, what I did was I calculated the moles, and then I divided the delta H per mole of NH3 into 2 moles. So to calculate that I did the negative 600.1 kJ divided by 2 moles, and then I got the negative 300.05, and then I multiplied that by the amount of moles I calculated.
And then, so what'd you get for your final answer?
Negative 415 rather than 563.
Yep, that sounds good. So let's walk through that slowly so everybody can follow along. So you said you found moles first, right? So that's what I'm doing. So we take our grams, and these are big numbers, so yeah, don't let the weird numbers scare you. So divided by 17 roughly, or our molecular weight. So we have 2.36 times 10 to the 4th divided by 17.031. And so now we get something crazy. So about 1,385 moles or so. 85, let's see, 0.7. And so then it depends how you want to do it. So from there, I just went ahead and set up kind of our proportion. So we did 1,385.71 moles. And then I just used our ratio from here. And so that means, right, it's for every 2, for every negative 600. Or you can do like what Dagan did, right, and found for every individual ammonia mole. So it doesn't matter, it gives you the same answer. So I'm going to use this relationship. So we had said for 2 moles of ammonia, that was 600 kilojoules released. And then if we multiply this, so times 600.1 divided by 2, since I didn't find my per 1. So it doesn't matter so much. So the negative is just showing us that it's released. But yeah, probably at the end we want to say negative to be consistent. So now we can say either negative 400 And then we could round, or we have sig figs. So, right, we only have, well, actually, we're given 4 sig figs, or 3 here. So we could round, so 416,000 kilojoules of heat, or something around there. So, right, without rounding, 415,700 and something. Or you can phrase it right, 416,000 roughly kilojoules of heat released. So again, the heat released is showing that it's exothermic with that negative sign matching. And so it should feel pretty straightforward, just like your stoichiometry, just involving enthalpy instead. All right, I think that does it for my kind of official review. But then, feel free to stick around, ask questions, turn in anything. And then I think people requested my presence on Wednesday, so I'll be there Wednesday, probably in lab again, just from 9 to noon. Just, come in, answer questions if you need. I can hand stuff back to you then as well. And then no grading errors. I'll be missing anything. All right, yeah, let me know sooner rather than later if something is amiss with the grades. Otherwise, I will see you Wednesday.